Welcome back to the class. So, in the last class you learnt about neighbor lists, which would help you increase the speed of molecular dynamics simulations significantly, a factor of 10 or 15, and that would enable you to run your molecular dynamics code for large number of iterations, which means large number of times. So, which means that you can follow the trajectory of n particles, where n could be 1000 or 10,000 over an extremely long period of time. And why do you want to follow it over a large period of time? So that you can calculate average statistical quantities from it, right. So, you could also run the code without your neighbor list, and then you can do up till 1000 particles at the most, and even that takes quite some amount of time if you run it long. But if you have above 1000 particles, running a molecular dynamics code without neighbor list is practically an impossibility. I mean, the code becomes extremely slow, and you will waste a lot of time waiting for the code to give you results, right. Okay. Now, suppose we have the trajectory, then what? Then we could calculate statistical quantities, as I have been telling you. In today's class, we shall discuss the discussion of how to calculate 3 statistical quantities just as an example. In that, you will calculate the pair correlation function, which essentially gives you information about the microscopic structure of the particles, right. And basically the Fourier transform of the pair correlation function is the structure factor. So, when you do a scattering experiment to find out the structure of a solid or maybe of a liquid, structure of a solid most probably has been taught in class, and you get your so called Bragg peaks. But here we have been studying liquids, dense liquids or gases, and if you basically measure using a similar scattering experiment the structure of the fluid, so structure factor, by measuring the structure factor, and then you can take the Fourier transform of it and calculate the G of r. On the other hand, you can also essentially put in a computer code, have a guess for the potential and calculate the G of r, given the match the densities as with that of your experiments, and check whether they are matching or not. If they match, you would say that you have a, at least in terms of structure, a reasonable or a good model for your fluid at the right temperature, and so on and so forth. The other thing which we shall calculate is the Maxwell-Boltzmann speed distribution, right. So, in a statistical mechanics course, you must have already learnt about the Maxwell-Boltzmann speed distribution, and what it gives is essentially the probability that a certain number of particles are moving with speed v and v plus dv, right. So, here this is the standard expression for p, where p is the probability density actually, right. And so, basically probability density has this expression. If you have any confusion, just look up your StatMech book. This is nothing but a prefactor into e to the power minus e being energy, and here you have kinetic energy by 2 kBT, right. Half mv square by 2 is kinetic energy, and is the energy of the particles by kBT, it is the Boltzmann factor essentially. So, we shall be discussing how to calculate that quantity, and PV dV, right. PV is the probability density, and PV dV being the speed interval is basically the number of particles moving with velocity v and v plus dv by n, the total number of particles, and that is the quantity which gives the probability of finding dn particles with speed between v and dv. So, PV is probability density and PV dV is the probability. And the last thing which we will calculate or I will tell you how to calculate is the so called diffusion constant and Maxwell-Boltzmann speed distribution. These two both are dynamical quantities, means it basically is a measure of how the particles are moving with time, right. So, so diffusion constant basically gives a measure of how much a particle has diffused or moved or got displaced. So, delta r square is a measure of the displacement of a particle. Of course, you have an expectation value here, you need that expectation value because you are averaging over many particles, right. It is an ensemble average quantity, because if a particle is diffusing, is doing a Brownian motion, you cannot predict how much that particle will move in the time interval t 2 minus t 1 in a certain time interval, say, which I have denoted by t 2 minus t 1. But if you average over many particles, then you can have an expectation value. What is the average expectation value? So, this is a measure of how much you can expect a particle to get displaced due to diffusion Brownian motion in time t 2 minus t 1. Here we are calculating PV dV, Maxwell-Boltzmann distribution. It is basically the number of particles moving with velocity v plus dV, right. So, it is impossible for you to calculate PV dV, Maxwell-Boltzmann speed distribution, if you did a Monte Carlo simulations, a Monte Carlo of lattice simulations of these particles, which is also possible, right. From there you can calculate the pair correlation function from if you simulate n particles, if you simulate the equilibrium distribution or the positional distribution of particles in a Monte Carlo off lattice Monte Carlo simulations with the same number of particles, you can get this quantity pair correlation function you can get, but you cannot possibly get Maxwell-Boltzmann speed distribution, because you do not have speed in Monte Carlo simulations. Please refer to your first lecture, where I gave a 15-minute 10-minute brief about how to do off lattice Monte Carlo simulation with particles, I mean basically the same kind of things. So, what molecular dynamics gives, as I said even in the first lecture, you have these dynamical quantities. So, instead of calculating just structural quantities, which you can also do in a Monte Carlo simulation, I have intentionally chosen two quantities which you can calculate using only molecular dynamics. Having said that, I will just add a small caveat. People do calculate diffusion constant in dynamics because it is about matter of displacement. Even in Monte Carlo simulations, where t 2 minus t 1 is replaced by the number of Monte Carlo iterations. So, that is also done, it is not unknown, but then you cannot really ascribe any time to the number of Monte Carlo iterations, but that is a topic for some other day and some other class. So, if you want to do dynamics, typically you choose molecular dynamics. Okay. Having said that, let me give you a detail of what is a pair correlation function. The pair correlation function is typically denoted by g of r, as I have written here, r minus r dash, where r is the position of one particle and r dash is the position of another particle, and it is also referred to the density correlation function. So, the density at point r, right, and the density at point r dash, and you are taking an average expectation value over it and normalizing by the average density square. Now, so in statistical physics books, you might more often find discussion about the density correlation function. That is what you typically calculate when you can calculate density as a function of space. So, I should not write equal to, I should be writing equivalent to, whereas in particle based simulations you typically calculate g of r which again tells you that if suppose there is a particle at point suppose r, then what is the probability, what is the, how are the other particles in its neighborhood distributed. So, basically with respect to this one particle, you are trying to find out the probability of finding other particles at a certain distance r. So, what you calculate in the Pea correlation function is essentially how the particles are distributed about one particular particle. Of course, you have to take an average to calculate the Pea correlation function. You have to take an average over all particles, because then it will say, I mean that Pea correlation function will give you the information that around any one particle, and all particles you assume to be statistically similar, around any one particle, what is the distribution of its neighbors around the particle. Okay. Now, just for an example, just suppose you are looking at this particular red particle here, and basically what you do to calculate the Pea correlation function is draw concentric circles which are marked in green here around this red particle, right, and you figure out within each of these concentric circles how many of its neighbors are there. Now, these concentric circles are of width dr, right, and they will be at distances r1, r2 and r3 and r4 and r5, further and further away from the center of your particle, of the particle in choice, and then you basically calculate within each shell, that is at distance of r1 and r1 plus dr, that is the basically the width of a shell, and r2 and r2 plus dr and r3 and r3 plus dr, how many particles are there. Okay, and this is what you have to calculate, and suppose you calculate this around particle number 1, suppose this red particle here is particle number 1, and you find out that particle number 2, 3, 4 and maybe 500 and 600 as the particles move around in space is around particle number 1, and you are calculating what is the average density of particles, how many particles are there at distance r1, r2, r3 on an average. When you are doing on an average, then as you do, you draw concentric circles around particle 1. Similarly, you can draw concentric circles around say particle number 2. You draw concentric circles and figure out how many particles are there at a distance of r1, at a distance of r2. When I say r2, I actually mean r2 plus dr. When I say r1, I mean r1 plus dr. So, how many particles are there within those concentric circles, and then you repeat that thing for particle number 3 and 4 and 5 and 6 and for n particles, where n could be around 1000 or 5000, it depends upon the number of particles in your box. And then to get an average, you can average over how many particles were there around 1, 2, 3, 4, 5, and you can average over these, right, because for each particle you can calculate how many particles were there at a distance of r1, r2, r3. And so, then you basically calculate an average over all these particles, right, and then you get a Pea correlation function for a particular microstate. Now, typically you would see that it will be extremely noisy, and it would be noisy, and you have to average over many microstates, because what you are calculating is a statistical quantity, right. How many particles are on an average are at a distance r, that is what you are trying to calculate. So, you not only average over number of particles, but you run the simulations, assume that it has reached equilibrium. It would have reached equilibrium when we had a discussion about how to check for equilibrium. Basically, kinetic energy, potential energy, etc. would fluctuate about an average, they will not evolve, especially if you have a thermostat, right. And assuming it has reached equilibrium, you can calculate the Pea correlation function, and it will give you an average number of particles that you find in a at a distance r on an average from any particle, right. It is basically telling you the distribution of neighbors around your any particle. So, how would it look? How should it look? So, here I have drawn schematically, of course, you will calculate it computationally, but here I have drawn it schematically how it would look for a simple liquid. Simple liquid, Leonard Jones you would call a simple liquid, where basically the potential is radially symmetric, because you could have also particles of a liquid which are rod like, but we are talking about simple liquids. So, we are not going there. So, for a simple liquid like Leonard Jones fluid at a suitable density, suppose around 0.2 or 0.3, what you would find is if I plot g of r, Pea correlation function, on the y axis versus r, the distance between two particles on the x axis, then basically for g of r would be 0 at very small distances till about the distance till r becomes order of sigma. And why is that? Because basically two particles, as in here, they cannot approach each other beyond the below a distance where the distance between their centers is approximately is equal to their diameter, right. So, why can't they approach? But because as you see, as the center between the particles becomes less than sigma, we have chosen sigma equal to 1, just to remind you. As the distance between the centers becomes less than sigma, this is a sharp r to the power 12 1 upon r to the power 12 strong repulsive force, which will make the particles move away from each other. That is a repulsive force. So, hence you see that nearly till up till sigma, the g of r is nearly equal to 0, which means two particles cannot approach each other below this distance 1 when sigma equal to 1. Well, you can so basically you do find, so the particles can approach distances of say 0.98 or 0.99 sigma. It depends upon the value, how strongly the potential goes up, and also depends upon the value of 4 epsilon, the prefactor of the Leonard Jones potential. But basically from around 0.98 the g of r starts to increase, which means that with rare occasions you do find where the distance between two particles, where the distance between the centers of two particles becomes around 0.98 or 0.97 or 0.99, but it is a rarity. And then you find a peak just beyond r greater than sigma. Here you find a peak, right. And the reason you find a peak is that if it is a liquid, then each particle will be surrounded by many other particles. So, if this is your central sphere, your particle of interest, just around it would be around 12 neighbors if it is a dense liquid, less if it is a less dense liquid, but you would find a large number of neighbors just sitting around it, right. So, what would be the schematic of a liquid? It would be something like this, surrounded by identical particles, right. So, somewhere here some are slightly farther apart, some are closer, and this is the approximate schematic diagram of a liquid. So, correspondingly just like around this particle, right, you find these other particles, you find a first shell of particles which is surrounding the particle of your interest, and corresponding to that you see a peak here, right. And if you have a large number of particles just surrounding your any particular particle, I mean this central particle could be actually any particle, because on an average you are calculating how many particles would you find at a distance r, where you should have to take the both the average over the number of particles and the time average, right. And if you have a if you have a large number of particles at say distance r1, right. So, which is basically a measure of your first neighbor shell, then just at a distance beyond r1, okay. So, slightly larger, so suppose r1 plus sigma by 2, sigma by 2 is the radius, right. So, if you are suppose finding a large number of particles at such a distance around the central particle, then you are not going to find the center of particles at such a distance, right, because most of the particles are just simply very close and sticking. There is a Lennard-Jones attraction, they are sticking to it. So, at a slightly higher distance around, if this was r1, then around so if this first shell this peak was at r1 at a distance and approximately r1 plus sigma by 2 distance, you are going to find the minima, because not the you will not find the center of other particles at that distance. But at the position of r2 suppose, which is the second neighbor shell. So, which is basically the second range of neighbors. So, you have a range of this is your first range of neighbors, and you would have suppose more neighbors somewhere sitting here, right. So, which is the second range of neighbors. For this particle, this would be the first range of neighbors, but for this particle, this is the second range of neighbor. You will find a large number of particles around distance r2. Of course, they are going to move around, they are going to fluctuate their position in space, and for that you will see a peak. Similarly, this peak, if you have one, then it corresponds to a third range of neighbors. Of course, if the density of the liquid is lower, then this peak will also be lower, because you are going to find fewer number of particles at distance r1 and a fewer number of particles at a distance r2. And at large distances here, right, at large distances what you are going to find is basically that it goes to 1, there is no correlation. So, on an average at very far distances at all distances there is an equal probability. So, the way Pea correlation function is calculated is basically you look at count on an average the number of particles that you have between r1 and r1 plus dr, that is within a shell. Then you divide it by the volume of the shell, because as you go farther and farther away, though your dr remains the same, for the volume of the shell is 4 pi r square dr. So, if you are going to larger distances, when r is large, 4 pi r square. So, basically the volume of the shell increases, right. And if you have a large volume of a shell, then you are likely to have a larger number of particles as well within that volume. So, to normalize it, to compare across distances, what you calculate is you normalize this dn, which is the number of particles between between r1 and r1 plus dr, and you also normalize by the volume of the shell, right, because you are calculating how many particles are there, what is the density of particles at a distance r. That is what Pea correlation function is giving you. What is the average number of particles? If you if you integrate over the volume of the shell, you will get the total number of particles which is within the shell at a distance r1. Yeah, and you normalize by the each volume of the shell, so that on an average you can figure out, oh, at certain distance r 1 I have a peak, which means there is a high number of particles around it. At a slightly larger distance r 1 plus sigma by 2 you have a low number of particles around it, low density of particles. You are normalizing because you have a larger shell, you might end up having larger number of particles, but density is lower. And finally, you normalize by the average density, so that at large distances r large, you can basically this g of r goes to approximately 1. So, then when if you have over large distances, you will lose any correlations unless you are very near the critical point, and for liquids this will basically go to 1, because it is normalized by the average density. It will, any particle will at far distances will see an average density, it will not have these correlations. Now, if this liquid was, if the density of the liquid is decreased, then what you will find is the peak will go down, or rather if you increase the density of the liquid, then this peak will increase, and you will have a higher peak, the second peak and the third peak, and so on and so forth. It also depends upon the temperature, how far the correlations can be seen, but always at large distances for a liquid or for a fluid, that is a liquid or a gas, you will see that the correlations have gone to 0. By the way, whenever I say distances, large distances, please you have to keep in mind that the largest distance that you can calculate is L by 2, which is half the length of the box. Technically root 3 by 2 if you measure along the diagonal, but typically you do not plot r larger than L by 2, where L is the length of the box, the size of the box, so assuming a cubic box. And if the box is not cubic, if L 1, L 2, L 3, the 3 different sizes are different, then you would typically plot up to the smallest dimension of the box by 2, right. And why is that? Because that is because of periodic boundary conditions. So, whenever you are calculating r, you have to also keep in mind that two particles could be at two ends of the box and yet be very close to each other while calculating due to the minimum image convention. So, whenever you calculate r, when you draw concentric shell and calculate how many particles are there around my shell, remember as the shell grows bigger and bigger, you have to account for particles which are on the other side of the box, right, especially if this particle is somewhere sitting, suppose this particle is sitting somewhere. So, this is your simulation box, say, right, and if it is here, then definitely this particle could be some close to some particle here. So, you have to be careful of that. So, while you have to develop the algorithm to calculate Pea correlation function, I shall just tell you that for the Pea correlation function, you shall need an array of length which is essentially decided by dr. Dr is what is the width of the concentric shell, and suppose the size of the box, assume a cubic box for simplicity, is suppose 30, then basically L by 2 is 15, and the length of this array by in which you shall store the values of gr while it is being calculated will be 15 or L by 2 divided by dr, right, because that distance you are going to half the length of the box, the maximum distance, you are going to divide it into small little segments of width dr. So, the length of this array in which you shall store the pair correlation function will be L by 2 divided by dr, And so, in this different boxes of the array or different indices of the array 1, 2, 3, 4 so on so forth. So, what are you going to store? Basically, when the index for the array is 1, basically you store how many particles are there between 0 and 0.5. For when index for the array, the index is 2, you basically store how many particles you find between 0.05 and 0.1. When the array is 3, you basically store how many particles you store between you can find on between 0.1 and 0.15 and so on. Now, if you have a liquid, you know that the values of N1 and N2 and N3 will be 0 till approximately the value of sigma. So, right, only when you find it's much farther down where basically you are checking how many particles are there in distance between 1 and 1.05, so which is somewhere here. That is where you will find a finite number of particles. Now, you have to calculate this array for each particle, then you have to average. Basically, there should be another array where you shall call average g of r or whatever, right, and there you shall similarly add all these numbers for another particle and so on so forth for every particle. So, then you will have an average g of r. G of r is anyway the pair correlation function g of r is anyway an average quantity. Nobody is typically interested to know what is going on around one particular particle. It is an average quantity, and so you have to average over all the particles in this array. Keep on storing for each particle, the end you have to divide by the total number of particles to get an average g of r at one particular microstate, and then as you allow the system to evolve, say you the system will access different microstates due to its time evolution, and then what you do is at each iteration, every 50 iterations, say, because one iteration to the other the positions will be rather correlated, it will not be a independent microstate, because the particles would have moved only a little v bit, right. So, after say around 50 iterations or after 100 iterations, where the so that the configuration of these particles are slightly different, you reach another microstate, independent microstate, and then again this value of g of r, you add this array to another calculated value of g of r, so that you can take a time average, right. So, time average is basically not very different from what we were doing in Monte Carlo. You are doing you are basically calculating some quantity at a particular number of iterations, and then that quantity after again a certain number of iterations, and again the value of that quantity again after a certain number of iterations, and at the end you were adding all these things up and dividing by the number of snapshots, right. Here the same thing you are doing, except that you are doing it for an array. So, it is a long array, and when you have to plot, you plot basically this average values of n1, n2, n3, n4, ni plus 1, particle averaged and time averaged versus distance, because the first one, this 1 into dr will say how many particles are there in how many particles are there between 0 and 0.5. Similarly, if you multiply the 8th or 9th or ith index of the array by dr, right, that will tell you how many particles are there in that box, and so on and so forth. Okay. So, that is how you calculate pair correlation function, that will be given as an assignment for different densities, and you shall see that if you decrease the density, then this peak the position of this peak also keeps on decreasing, and so that when it is a gas, right, it is really dilute, then you basically the pair correlation function beyond distance sigma becomes practically equal to 1. So, here I have shown a very small peak, and thereafter it becomes practically 1 here all over, and if it is a real gas it would be 0 up till distance 1 and 1 onwards. So, for r equal to 1, and after r equal to 1 the value of g of r will remain 1 from r greater than 1 to all large distances. This is half the length of the box. What does that mean? That means that the probability of finding a particle at any distance greater than r equal to sigma is the same. It is an average density. There are no local spatial correlations as seen in a liquid. In fact, microscopically that is how you differentiate between a liquid and a gas, because for a gas the pair correlation function for r greater than sigma will be absolutely equal to 1. Okay. So, what about the next quantity? If you have understood how to calculate pair correlation function, then calculating the Maxwell-Boltzmann speed distribution should be a cakewalk, because in the Maxwell-Boltzmann speed distribution, where the probability density function P v is, this is the form which you can check from your statistical mechanics book, and if you plot it, this is how it looks, right. There has to be something missing here, and I had missed a v square even here if I am calculating the speed distribution. Okay. And because this quantity is an exponential, where with increasing v it is sharply falling, but v square is an increasing function, you get a peak, right, and it is not a symmetric function. Speed cannot be less than 0. So, it has to start from 0 to larger and larger values. And when I say that you have to calculate P v in the computer simulations, this again means that the particles are moving around in space, they are colliding, hence they are exchanging velocities with each other, there is momentum transfer from one particle to the other. So, hence each particle will keep on changing its speed as it moves along. Moreover, on an average, different particles will be moving with different speeds and of course, velocities itself. So, on an average, to calculate P v, you have to calculate how many particles d n, how many particles d n are moving with speeds between v and v plus d v, right. So, what is v? V is nothing but v x square plus v y square plus v z square root. And just as previously, just as in pair correlation function, you have to average over different times, right. So, you allow the system to evolve as the particles move around every 50 iterations or every 100 iterations, depends upon the value of d t. As soon as you have a different microstate of the system, you calculate for a particular microstate how many particles are moving with velocity v and v plus d v, and of course, this d n quantity you average over different microstates at different times. So, finally, you keep on adding an array, the value of d n 1, 2, 3, 4, 5, 6 for different values of velocity, and each value you calculate at different times, average them divided by the total number of snapshots, not very different from what we did in Monte Carlo or the previous step. So, here you will again have an array, where the first index of the array will store how many particles are moving with speed 0 and 0.05. So, suppose d v is 0.05, and then how many particles are moving with speed between 0.05 and 0.1. How many particles are moving with speed between 0.1 and 0.15, and so on so forth. So, again what will be the size of the array, because you have to initialize it, how can you estimate it. Now, we were working with essentially kBt equal to 1 and mass equal to 1, and you know that the position of this peak of the Maxwell-Boltzmann speed distribution is root 2 kBt by m, right. So, this point, if kBt is 1 and m equal to 1, so the position of this peak will be at root 2, right. Now, if the temperature changed, if the temperature became less, then what you would get, of course, then the peak will also shift. So, you will get a different Maxwell-Boltzmann distribution. So, here this data, this one is for essentially temperature T1, the one with dots where this one is with temperature T2, where T2 is greater than T1. And of course, the probability under the curve, which is PV dV, right, has to be, and the sum of it has to be 1, because it is probability, right. This is probability density function, that is probability divided by dV, right. What is probability? It is number of particles moving with velocity v1 and v1 plus so v or v plus dv divided by the total number of particles on an this n will be fixed, this dn is the quantity whose average you have to calculate, and then all that you have to do is basically divided by dV, which will give you the probability density. Because if you chose dV to be smaller, say instead of 0.05 you chose it to be 0.001, then you are going to find a large fewer particles between 0 and 001, right, because all the particles, suppose n1 was the number of particles, an average number which was moving with velocity with speed between 0 and 0.05. Now, if you choose your dV to be 0.01 say, then this n1 particle will be divided into 5 partitions, right, because now you are calculating how many particles are moving between 0 and 0.01, 0.01 and 0.02, between 0.02 and 0.03. If we add up all these numbers, the average from 0 to 0.05, then you will get. So, you have to divide by dV, be aware of that, right. Okay.